Welcome in Dark Core. The ability to travel through time has long been a subject embraced by science fiction, and of course, has been debated by physicists for decades. While the argument continues over whether traveling back in time is possible, researchers have determined that traveling to the future is definitely possible, and you don't need a 1.21 gigawatt flux capacitor-powered DeLorean for the journey. Real-life time travel occurs through something called time dilation, which is a property of Albert Einstein's special relativity, an explanation of how speed affects mass, time, and space. It was Einstein who was first to realize that time is not constant, but instead slows down as you move faster through space. Basically, what that suggests is that time is an illusion that shifts relative to the observer. If you were able to travel the speed of light, you would experience time much more slowly than a stationary observer. Even astronauts in space age slower than we do here on Earth. We'll talk more about those things in a moment. It's important to understand how spacetime works if we're going to time travel. Our understanding of time and causality comes from Albert Einstein's general relativity. Einstein had to re-envision space itself and coined the phrase spacetime, which fuses together the three dimensions of space and the one dimension of time. Instead of space being a flat and rigid place, Einstein thought of space as being curved and able to form gravitational dips, called gravity wells, around large celestial masses including planets, stars, and massive collapsed stars called black holes. Gravity bends the fabric of the universe called spacetime, not just near black holes, but in any gravitational field including Earth's. This is important to understand, because the further away from a gravitational source you are, the faster time for you will pass. But it's also possible there's something else lurking in the universe that bends the fabric of space-time. It was Albert Einstein and another physicist by the name of Nathan Rosen who were also studying the inescapable pockets of space we call black holes. They discovered, theoretically, that the surface of a black hole might work as a bridge connected to a second patch of space. This became known as an Einstein-Rosen bridge, or wormhole. In Einstein's theory of general relativity, creating a wormhole is pretty straightforward. You simply take a black hole and connect it to a white hole, and the result is a tunnel through space-time. If you've never heard of a white hole before, we got you covered. White holes are purely hypothetical objects that astronomers are trying to figure out how, and if, they could form in space. In theory, a white hole is believed to be a time-reversed black hole, a region of spacetime where matter would appear and spit out light and matter, rather than trapping and crushing matter into a singularity like a black hole does. If it's the exact opposite of a black hole, we should be able to see them by the different types of light or radiation they give off. In fact, some researchers believe that some black holes we've found could actually be white holes in disguise. Wormholes are thought to be interdimensional portals that bend the fabric of spacetime and connect distant corners of the galaxy. Wormholes require extreme warping of spacetime, and would require powerful gravitational forces to exist. This is why some astronomers say a good place to hunt for wormholes is near supermassive black holes that lurk at the center of galaxies, like our own Milky Way's Sagittarius A*, pronounced A star. Einstein and Rosen continued to study the idea of wormholes, but big challenges came up during their work. The first challenge is that in general relativity, the gravitational attraction of normal matter passing through a wormhole would close the tunnel shut. Therefore, making a stable wormhole that stays open would require some type of exotic negative matter to keep the tunnel open. The second problem is the process needed to create the wormhole, and finding the exotic negative matter to stabilize it cannot stray too far from current rules of physics. Negative matter doesn't appear to exist in the universe, but that doesn't mean it doesn't exist. To stabilize a wormhole, the traveler would have to experience a region of negative energy that would balance out the positive energy mass of the traveler. That sounds nearly as impossible as time travel and wormholes themselves. But in 2017, physicists discovered a way to prop open wormholes with quantum entanglement. This peculiar nature of entanglement would provide the negative exotic matter needed for wormhole stability. It's an interesting idea, since a wormhole has never been discovered. And unfortunately, if wormholes actually exist, they would be incredibly unstable. As soon as a wormhole formed, they would instantly collapse, or their gravitational strength would rip them apart faster than the speed of light, making them pretty much useless as a shortcut through places in the universe. It could be that wormholes pop up all around us, but collapse so quickly we never get a chance to detect one. Even if we found a wormhole, we need to remember that the universe is vast. If you've seen the movie Interstellar, you'll remember that the wormhole built or created by unknown beings to save humanity was near the planet Saturn in our solar system. Not a convenient place to put a wormhole that needs an incredible amount of negative energy to keep it stable, since it would take the fastest ship almost 4 years to get there. By comparison, it took the New Horizons spacecraft 9.5 years to get to Pluto. If we spotted a wormhole, and for some strange and unknown reason it was stable and didn't evaporate instantly, we currently don't have the ship to get to it in a timely manner anyway. It would be really convenient if one popped up next to us, say between us and Mars. But let's say a wormhole did pop up and was close enough for us to explore, and we had the ship. Could we survive a trip through a wormhole? At this point, no one knows. And of course, no one knows if going through a wormhole would be a one-way trip or not. You may never come back, and by the time you did come back, depending on how long you were gone, there might not be anything to come back to. You'd also have to consider that you'd never see anyone you know ever again. Some physicists claim there is a way to send a person through a wormhole, and not only would they survive, but they could traverse the entire Milky Way galaxy in a second, and those who didn't go through the wormhole, thousands of years would go by. But is time travel possible without wormholes? If you're talking about traveling forward in time, then yes. But it would take an incredible amount of energy and speed to pull it off. We mentioned astronauts in space earlier. Cosmonaut Gennady Padalka spent 879 days in space. When he arrived back on Earth after being in space for 2.5 years, Padalka found himself in the future by 1/44th of a second. He literally traveled into the future by coming back to Earth. Now, a fraction of a second isn't mind-blowing stuff, but it is proof that it is possible to travel forward in time, and Padalka holds the current time traveler record. However, we should keep in mind that the cosmonaut was traveling at just 27,358 kilometers per hour, 17,000 miles per hour, and wasn't too far from the Earth in geostationary orbit. But what would happen if something could move much faster? Scientists have been using the Large Hadron Collider to send subatomic particles into the future. In fact, the particle accelerator has the ability to propel protons at 99.999999% the speed of light. At this speed, the relative time of protons is moving about 6,900 times slower than their stationary human observers. Back to the movie Interstellar, remember where the main character experiences big time dilation and returns to Earth to find his daughter, an old woman in her last days, lying in a hospital bed. The farther and faster you travel away from Earth, the faster time would slow down for you, but time would stay the same for an observer on Earth. For example, let's say we wanted to visit the Earth in the year 3000. All you would have to do is get on a spaceship and travel at 99.99% the speed of light. And let's say that your destination is Kepler 186f, which is about 580 light-years from Earth. If our astronauts traveled close to the speed of light, it would take them about 580 years to get there. After arriving and getting a quick bite to eat and a restroom break, our astronauts head back to Earth, which would take another 580 years. In total, we're looking at 1,160 years for a round trip. You might be thinking, our astronauts aren't going to live long enough for the trip. Well, here's the mind-blowing thing about time dilation. Since the space crew was moving so fast, the resulting time dilation of their trip wouldn't seem like 1,000 years to them, since their internal clock has slowed to 1/100th the rate of clocks on Earth. The spaceship crew would only age about 10 years because they are hurtling through the cosmos, while more than a millennium would pass for us. So you see, it could be possible to time travel into the future, but for now huge engineering obstacles are staring us in the face. For one, we're not even close to having any kind of spaceship that can travel the speed of light. Of course, we need to come up with a solution for the main obstacle, which is figuring out how to harness the incredible amount of energy needed to propel the ship to the speed of light. The human race has a long way to go yet when it comes to fully understanding time and gravity. Perhaps one day we may figure out how to travel the speed of light, or we may be able to detect and find a wormhole one day that is close enough to us, and send astronauts through it to find out what's on the other side. That said, we're curious if our viewers would be brave and volunteer for such an expedition. Would you go? And if you could travel through time, would you go back in time, or forward into the future? Time travel will be very difficult, and it might create crazy paradoxes. Let us know if you want to see a video on these topics. To keep up to date on all the cool things happening in our universe, make sure to stay tuned here by subscribing, and slap that like button if you enjoyed the video. Thanks for watching Dark Core.